Okay, so now we're moving into chapter 13, and we're actually going to start with the next type of integral. So far we've done single integrals in Calc 2, double integrals and triple integrals. And now we're going to think about what if we want to integrate over a surface that's sitting somewhere in 3D. So suppose you have this surface here where we're going to call this whole region S, and this is a capital S we're going to be using. And suppose that the density at any given point on this surface is this delta xyz. And we could ask, what's the mass? And we're calling this a shell because it's not a three-dimensional, or it's not a 3D filled-in object. It's just the outer shell of an object. And the units here would be mass per unit area. So we could ask, what's the mass of the shell? Okay, so first, we are going to, just like we've done all along in this class, chop up this region S into little sub-rectangles of area delta S. And I'm going to be using a capital S here. I'm going to try to make it look really capital. And then we would like to approximate the mass of each sub-rectangle. So notice that the mass, like if I just wanted, let's highlight here, if I just wanted the mass of this little sub-rectangle here, then I would need to take the density at a point there in the sub-rectangle times delta S. And so how we denote exactly where I am on this, what's easiest to see is that because I really only have a two-dimensional surface that's sitting in three-dimensional space, I can use kind of moving along here as counting in I, like I is 1, I is 2, I is 3, I is 4, and then I can count up this way in J. And so I can get to a point right here that's going to have X, Y, and Z coordinates, but I could write them in terms of where they are in terms of I and J. So I'm going to call it X sub ij, Y sub ij, Z sub ij, just to let you know where we are on this particular little surface. And then there's corresponding X, Y, and Z points there. And this is just going to become important because when we go add this up, it means that we're only going to need two sums, because technically we can actually parameterize the surface just in terms of two variables. We're going to not do it via parameterization in this class, but you'll see the book does cover it that way. And so we have an extra handout, separate handout for you to be reading the theory behind when you don't use parameterizations. It's fine if you want to learn how to parameterize, that's great. We just didn't include it in the scope of this class, and so we're going to show you how to do this without parameterizing the surface. Okay, so then we are summing up the masses of each little piece, and that's where we're getting this, where I'd be summing in I and in J. And then to get the exact mass, we'd now take the limit as delta S gets smaller, which is n and m is going to infinity. Okay, and this is a limit of a double Riemann sum, which we know we can write then in terms of a double integral. And writing it as a double integral, this is going to become an integral over my surface S, and then my integrand is going to just become my density ds. And we don't know how to evaluate this yet. We're going to talk about how we actually evaluate this type of integral. But you can notice we're defining it by Riemann sums, limits of Riemann sums. And then to actually evaluate, we're going to have to change variables and get everything in terms of the same variables. Because right now, my ds is not at all in terms of x, y, and z, and my limits are not in terms of all the same variables. I'm going to need to get everything down just to two variables, and we'll show you how to do that. Okay, so and this is what we define in general as the surface integral of a scalar function. So this is one particular example finding the mass of a shell. But in general, we'll define the surface integral of a scalar function to be this double integral of any function inside. So it doesn't just have to be density. It could be temperature, it could be lots of other options. And then ds. And this is a capital S. Okay, this is the surface integral of f over the surface S. All right, so let's see how we can do this and like how we can find basically a Jacobian for this ds and rewrite it in terms of just two variables, not three, so that we can evaluate our double integral. Okay, so to actually evaluate this scalar surface integral, we're going to need to change variables. And the first step we're going to use is to write our surface S as one level surface of some function of three variables. Okay, so let's let, for example, we can let S be written as g of x, y, z is equal to some constant. Okay, so that's just another way of thinking of this surface. And we did this back when we were figuring out normal vectors for tangent planes. We rewrote surfaces as one level surface. It's that same idea. We're going to see how we use that here though. Okay, and then we're going to take the surface S and we're going to project it onto one of the coordinate planes. And so in this picture, we are showing it being projected here onto the XY plane. Let's call this region R just to be consistent with our notation. But we're going to see how we can choose different coordinate planes to project onto. But in this case, in the picture, we're just projecting onto the XY plane. We're going to let P hat be a unit vector that is normal to whatever plane you project onto. So in this picture, P hat would just be K hat, because in this picture, the normal vector is just pointing in the Z direction. Okay, but then we'll show you other options if we were to project onto the other planes. And then I need to find ds, which is basically like figuring out what's my Jacobian going to be. Now, normally, I think you may recall, we've shown you can find the Jacobian by doing the determinant of this matrix, but that's only going to work with surface integrals if you parameterize the surface. And that's not in the scope of how we're teaching it this semester. So you won't see a determinant of a matrix here as the Jacobian. We're just going to do it all geometrically. And it will be equivalent to what you would get if you did parameterize and you did find the determinant. And that's what's shown in the textbook. So if you're curious, you can learn that other method. But we're teaching it this way because it's actually much more general and doesn't require needing to learn how to parameterize surfaces. All right, so the first thing that we're going to do is take a little tiny piece here. I'm just going to re-sketch a little piece. Okay, and so this is supposed to look like just a tiny piece of the surface up above where I'm going to call this area delta S. And then we're going to call this area down here, which is like the shadow of this delta S, the projected area, and we'll call this delta A. And our question is, how can we relate the blue area to the yellow area? And they're not the same, but I'd like to know when I switch variables and I change from this yellow surface by actually integrating over the blue surface instead, what the difference would be in the area, so I can account for any changes. Basically like exactly what we do with Jacobians. And the idea is that this is a super small delta S. So if I were to draw these two vectors along the side, let's call this A and this is B. For a really small delta S, the magnitude of this parallelogram, A crossed with B, would actually equal delta S. So we're going to assume it's just small enough where that's a good enough, because we're going to take a limit eventually, so this would be a good approximation. So just assuming it's small, we can say this yellow area is given by this cross product of these two vectors. And now notice, if I actually take the cross product, I'm going to get this vector that is normal to both here, and whose magnitude is the area of the yellow region. So let's write that. A cross B is going to be the magnitude of A cross B, which is just delta S. We'll write it up there. And then times a vector in the direction, like a unit vector that points in the same direction as A cross B. Interestingly, we actually know a vector that points in the same direction as A cross B, because up above we defined this surface as one level surface of this function g, which means that the gradient of g at any point has to be normal to the surface. And so the gradient of g is going to be pointing in the same direction as this cross product. And we can use this to help us find this unit vector, because a vector that points in the direction of A cross B but instead is a unit vector is just going to be the gradient scaled to be a unit vector. And then we can replace the magnitude here with just delta S, assuming that once we do this small enough that the magnitude of that cross product will actually be the same as the little yellow area. Okay, why are we doing this? So let's see. What we're trying to get to is a relationship between the yellow and the blue areas. And one more piece that we can add into this puzzle is that we have this vector p hat, which we're defining to be a vector that's normal to the plane where we've projected. In this case, it's normal to the xy plane. I can rewrite that vector. Let's move it up here. Oh, let me get a little bit more space. I'm going to just relabel this delta g over here. Okay, so I can translate this and rewrite p hat right up here as well. And it turns out, and this is not completely obvious, so if you're thinking, where did this come from, that's okay. It turns out that this blue area we can get directly out of a projection. If we project the cross product vector onto the vector p hat. So this is going to be equivalent to the magnitude of the projection of A cross B dotted with P. And this is the projection because it's just a unit vector. P hat is just a unit vector. So that's actually just going to help us show visually. We take this, we project it onto here, and this is going to give me this magnitude here of the gray vector will actually correspond to the blue area, where the magnitude of the purple vector corresponds to the yellow area. And this should look like it's actually projecting right on here, 90 degrees. Okay, so we're going to use that fact that we can get delta A by taking this projection to help us rewrite delta S in terms of delta A. So notice delta A is the magnitude of A cross B dotted with P. But we have A cross B up above. We rewrote A cross B as this. So let's replace it here. This is delta S, gradient of G. And the good news is once we've done this once, you won't have to rederive it every time, but I just want you to see where it's coming from at least once. Dotted with P. And we can notice when we take that magnitude, the delta S can come out front because that's always going to be positive. Really the only part that we're still taking the magnitude of is this gradient of G dotted with P, because this denominator here is going to always be positive. All right, and so this gives us a way to relate delta A over here with delta S over here. Okay, so multiplying both sides by the magnitude of the gradient of G divided by the absolute value of the dot product between P and the gradient of G, and then that's times delta A. Okay, and so in the limit, once we actually put this inside our double integral, we're going to get that ds is equal to this whole quantity times dA. So I can rewrite that down below here. And then we're, oh yeah, let's put it here. So i.e. ds is going to be this whole quantity. This is basically the Jacobian. We just found it using geometry in this case. And then you will rewrite your integrand in terms of this keeps flying away on me. There we go. Rewrite the integrand in terms of and the Jacobian in terms of the two variables where you projected, using the fact that you can rewrite your surface, your function, as a level surface. This is, I'll show you in an example what I'm doing here, but these are just giving you the main steps. And then lastly, you'll determine the limits of integration of the projection, and that'll just be like a normal double integral that you've done before in the plane. So the biggest thing is just doing this whole change of variables in order to rewrite it as a double integral over the little blue area above, because we know how to set up bounds for double integrals once we're in the xy plane. All right, let's try it with an example.